Hey, so in this video we're going to talk about balancing redox reactions. I know that you have a lot of experience in balancing traditional reactions, and some of the reactions that you've balanced before are actually redox reactions, but there's a certain type of redox reaction where it's a little bit more complicated than types of reactions that we've done in the past. So a lot of times when we talk about balancing a reduction oxidation reaction, they just mention they might just mention the actual species that are getting reduced or oxidized. All right. So in this example right here, we're going to talk about a reaction where permanganate ion is going to get converted into manganese plus 2, and oxalate ion is going to get converted into carbon dioxide. All right. So the one thing about these reactions is that they're always going to occur in aqueous solution. Generally, they're going to occur in acidic solution. Sometimes they can occur in basic solutions. But as far as the IB is concerned, they only expect you to be able to do this if it occurs in either acidic or neutral conditions. All right, we're not going to get into the topic of how you would do this with under basic conditions. It can be done, but we're just not going to do it in this class. So as we said, in this particular reaction, we're going to talk about how permanganate is going to get reduced to make manganese ion, and oxalate is going to get oxidized to make carbon dioxide. All right. So first of all, the first step here is to separate the reaction. First of all, when you do this, there are actually some things that are involved in this reaction that aren't shown here. All right. Generally, it's going to involve either some water molecules or some hydrogen ions, H pluses, and they're not shown when we're just showing the things that are getting oxidized or reduced. All right. So this method is going to show how that occurs. All right. So the first step is to separate the reaction into separate oxidation and reduction half reactions. All right. So you'll notice that when I've shown this reaction here, I've got some writing out to the side, and all I'm doing here is I'm writing oxidation numbers beside any of the non-oxygens, all right, or non-hydrogens if any of these were to have any. All right. So if you do this for permanganate, you would see that the manganese has got a +7 oxidation number, and manganese plus 2 has got a +2 oxidation number. So a +7 going to a +2, that's a reduction. So the manganese is getting reduced in this process. All right. So when we do our reduction oxidation half reactions, we're going to show that as our reduction half reaction. If you figure out the oxidation number of the carbon in this oxalate ion, and by the way, you're not expected to know the name of that ion, so you would figure out that its oxidation number is +3, and if you figure out the oxidation number of carbon in carbon dioxide, you would see that it's +4. So +3 going to a +4, that's going to be an oxidation. All right. So the first thing that we're going to do is we're going to separate these two things into a reduction and an oxidation half reaction. All right. So as we said before, permanganate going to manganese +2 is the reduction. The oxidation is oxalate going to carbon dioxide. And one thing that might strike you as a little bit odd here is that we haven't shown electrons. All right. And when we're doing this method, we're not going to worry about the electrons until a later step. So don't worry about the fact that we don't have a charge balance here, and we haven't shown electrons. We'll do that in just a second. All right. So the next step that we're going to do is that we're going to add coefficients to compensate for any non-oxygen or hydrogen atoms. All right. So if we take a look at these reactions here. All right, let's take a look at anything that's not an oxygen or a hydrogen. All right, so we got manganese here, and we got manganese here. So there's one manganese here, one manganese here. So that part right there is fine. All right. So in this part in the reduction half reaction, we don't need to add any coefficients to that. But if you take a look at the oxidation, we've got 2 carbons here, but we only got 1 carbon right here. All right. So what we're going to have to do is add a 2 coefficient so that we have the same number of carbons on both sides. All right. So that's what we've done here. All right. So you might notice, hey, we don't have the same number of oxygens on both sides, but we're not going to worry about that. We're going to take care of that in the next step. All right. So as I said, what we do in the next step is we're going to add water molecules to one side of the reaction to compensate for oxygens. All right. So let's go back to this reaction right here. All right. So if you look at this, we've got 4 oxygens right here, and we've got 0 oxygens on this side. So what we're going to do is we're going to add 4 H2Os to this side right here. Each water molecule has a single oxygen atom. All right. So if we add 4 H2Os, that's going to add the 4 oxygens so that we have the same number of oxygens on both sides. All right. All right. So there are our 4 H2Os. All right. You'll notice there's some H pluses over there. We'll talk about that in just a second. All right. So looking at this, we've got 4 oxygens over here. And if you count it up over here, we've got 4 oxygens on this side too. So we don't need to add any water molecules to either side of this reaction to balance that out. All right, so that one just stays as is. All right, so the next step is to add H pluses to the other side of the reaction to compensate for hydrogens. So this is where we go back and we say, all right, well, we added the 4 oxygens here so that we have the same number. Sorry, we added 4 water molecules so that we have the same number of oxygens on this side as we did on this side. But now we would have, if we didn't have this right here, the H pluses, we would have more hydrogens over here than we did over here. So the process is going to always be the same. You add the water molecules to balance out the oxygens, all right, and then you add H pluses to the other side to balance out the additional any discrepancy in hydrogens. All right. So at this point, we're now at the next step where we are going to add electrons to one side to give a balance, a charge balance on both sides. So let's take a look up here. If we okay, so I meant to cover up the electrons here. So let's pretend that the electrons are not there yet, and we'll just focus on the rest of it. All right, and that's just carrying down what we had up here before. All right, so if we added up the total amount of charge from the left side of the reaction, that would be a +7 charge. We added up the total amount of charge from the right side, that would be a +2 charge. All right, so how do we make the total amount of charge on both sides the same? What we're going to do is we're going to add 5 electrons to the left side. So if we had to do the 5 -1 charges plus this +7, that would add up to a +2 on this side, which would make it the same as what you have on the right side. All right. And again, if we just look at the part that we bring down from up here, you'd notice that there is a total of -2 charge on this side and a 0 charge on this side. So in order to get those charges to balance, we need to have 2 electrons over here. So now with the 2 electrons, we have a total of a -2 charge on the right side, and that will balance what we have on the left side. So the next step is to compare both reactions, and if the number of electrons on the opposite sides don't equal each other, we're going to multiply each reaction by a whole number so that the electrons will equal each other. All right. So if you take a look at these at these 2 reactions, notice that we've got 5 electrons as a reactant on this reaction, and we got 2 electrons as a product on this reaction. And what we eventually want to do is to be able to cancel out the electrons. But in order to do that, we would have to have the exact same number. All right. So how are we going to do that? Well, we want these things to be the same. So the way that we're going to do that is we need to multiply this and this by some coefficient so that they're going to equal each other. And hopefully you can see, all right, if we multiplied the top one times 2, that would give us 10 total electrons. And if we multiply the bottom one by 5, that would give us 10 total electrons. So the thing is, we got to multiply the entire reaction by that coefficient in both cases. So if we do that here, we will get this reaction, and multiplying this guy right here by 5, we would get this reaction right here. So notice what that does for us is that we now have the same number of electrons as a reactant in this reaction and as a product in this reaction. So when we add these reactions together, we can cancel those out, and that's what we're going to do in the next step. Is we're just going to cancel those out, and we're going to bring down all of our reactants from both the reduction and the oxidation half reactions, and all of our products as well, and that should give us our final product. All right. And one thing I skimmed over before, anytime you see something which is charged, has a charge in any of these, you can assume that it's aqueous. All right. And some of the common things like carbon dioxide, you should know that that's going to be a gas if it's in water. So the L for the water stands for liquid. It would be okay to put aqueous. There's a question: is the water a solute in a water solvent, or is it just some extra water? It's really not that important. So the last thing to do here is just to check to make sure that you've got the same you got the same number of atoms on both sides. All right. So if you've done this correctly, we should have the same number of manganese atoms on the left as we do on the right. We should have the same number of hydrogens on the left as we do on the right. We should have the same number of everything, just like a normal balancing reaction. All right. So I know this is a little bit steppy. Don't feel bad if this is feels kind of complicated at first. With practice, you will. I'm confident that you will be able to do this. And please have these steps right here handy when you're trying practice problems with this, because it'll take a little bit of practice. So good luck with that, and we'll talk more about this later.